nickel-based filler metal. And another category was failure along a line of globular carbide formed in service, again next to the fusion line. So this was observed while the weld was carried out with the nickel-based filler wire. Another type of failure was attributed to the oxide notch formed on outside of the tube at the weld to low alloy junction. You can see here an oxide notch. The notches generally do not propagate to failure, but can, in the case of a thin wall tube subject to high bending stresses, which can initiate a failure. So what they observed was the nickel joint was giving 3 to 5 times longer life, while the stainless steel joints, their life was very limited. Another finding was that a wider bevel on the ferritic side also extended an increased service life. There is one more case study on the nodular cast iron to steel. So if you see here the steel, the coefficient of linear expansion is 12.1, the cast iron is 10.8, and these are joined by nickel which has got 13.3, so there is a considerable difference. And you can also see the microstructure of the cast iron and carbon steel on the left hand side. So you can see how different they are, and the challenge is to join them. And one should also be very conversant of the iron carbon diagram as a metallurgist while you handle such multiple variety of materials to join. So what was observed was there is huge crack at the HSZ when they tried welding it without a buttering layer. And the hardness also you see in the heat embedded zone without a buttering layer with the different consumables like ENICA1, FEC1 and 7018. The hardness were quite high, though it was little less with 7018. But when a buttering layer was produced and then subsequently it was welded, the hardness were relatively low, and that is how you should tackle the situation. So even today this is a real challenge to weld these two, because you have a different microstructure, you have different strength, and different coefficient of thermal expansion. So a lot of study goes behind while you derive such procedures. Few more examples of hydrocracker reactor, where you have 2 quarter chrome 1 moly quarter vanadium which you need to join to a stainless steel 347. So again, if you see the difference in the yield strength of these two materials, elongation, they are vastly different, and the thermal conductivity, you can see how they differ, and even the thermal expansion coefficient. For alloy steel, if you consider 12.5, and for stainless steel it is around 16.5, there is a huge difference. So the weld procedure which you develop has to be thoroughly studied and verified before such things are put in application. And this is a very common joint which comes in a hydrocracker reactor, and generally these are handled with the Inconel 600 buttering on the chromoly vanadium side, subjected to very high temperature PWHT. To add to complications, you also have stainless steel weld overlay on the ID. So the joint which you produce subsequently, you will have, that rather 3 welds to handle. One is your buttering, one is your 347 weld overlay, and also the groove joint which you are filling it up with Inconel 600, and your stainless steel 347 on the right hand side. So you handle 4 materials plus your chromoly vanadium. So you handle 5 different variety of materials while you produce this joint. So proper metallurgical study is very much essential, or else you will end up in big problems either in the shop floor or while this is being subjected to service. This is another example in case of reactor where you have very critical tube sheet wells where there is an overlay of Inconel on the tube sheet and your tubes are of duplex. So it becomes much more complicated. How do you join a duplex to a stainless steel? Generally these are done with Inconel 600 and you see the difference in again the basic physical properties and the mechanical properties as shown in this table. You have some other cases where you need to join stainless steel to modify 9 chrome 1 moly for a steam generator. So if you see the again here the physical properties between 9 chrome and 316L. Suppose I take the elongation, one is of 30 and the other is 14. Thermal conductivity again 15 and 50. Thermal expansion 16.5 and 12.5. So how you tackle this situation? So the best way is to introduce another material which are compatible to both, which has properties intermediate between these two, and the right choice being Incola 800, which completes this table. You can see which has a property in between these two, and you can produce a very successful joint. And still lot of researches are happening in this joint where you need to join stainless steel to Inconel and Incolloy and then Incolloy to modify 9 chrome 1 moly. Another combination in a tube to tube in a reactor where you weld stainless steel to Inconel 600, and if you see here there is a requirement of producing these welds defect free with orbital welding technique, because what you require is a totally defect free joint as the service is highly critical. Again a copper to nickel aluminum bronze. So here also there is a huge difference in the properties. So the consumer which you select needs to balance or rather take care of both the best material so that it can suffice the purpose. Another waste heat boiler which is generally used in the refinery or in the fertilizer. Again you have 2 quarter chrome 1 moly on one side which is joined to SS347H. So generally you do it with an Inconel buttering, subjecting the 2 quarter chrome to PWST and again join with Inconel 600. So what I would like to bring out here is there is a lot of science behind all these joints, lot of thought process, lot of studies, lot of researchers has gone into while deriving this procedure, and many things has kept evolved over a period of time based on the failures which has happened in service at various petrochemical plants, refineries. So and the field is still evolving because still there are a lot of challenges in the dissimilar metal welding. So as we are getting into the conclusion part, you need to take care of the critical aspects like welding process, welding consumable, the welding technique, within welding technique, joint design, dilution, heat input, the interpass, what PWST you are subjecting, and what NDT you are planning to do on the joint, and what physical testing are you subjecting it to during your procedure qualification. The welding practices like whether you are doing a buttering or not, how you are going to select your welding consumable, is it required to add a transition material which similar to what we saw in the case of steam generator. And also there are possibilities to use advanced welding processes like electron beam, and you have a lot of solid state welding processes. So we saw this in detail. The best way is to produce with an Inconel buttering and a subsequent joint with Inconel. And regarding the consumable selection, based on the material combination, you need to plan things around, like whether it's a ferritic steel to austenitic stainless steel, and what is the temperature my weld will be subjected to. Like as a thumb rule, less than 315 you can go for a 309L type, and more than 315 nickel is preferred. 310 is a good option, but when you have PWST, that is not the right option. You need to consider those aspects. And nickel is not the solution to everything, because nickel you cannot use in hydrogen service, H2S service. Nickel has got enormous advantages in case of dissimilar joint, but there are certain cautions or precautions rather that also need to be addressed while you decide or rather plan to use nickel for a dissimilar joint. Possibility to add a transition material similar to the steam generator. Suppose you have to join a copper to steel. Again, you can think of a nickel being added. And lot of good practices during your welding technique, like the process which you select, the bead sequence you plan, the amount of bead overlap you give. You need to get into all such nitty-gritties while deriving your weld procedure. So there are, as I explained, there are high energy beam welding processes like laser beam. For joining materials with considerable difference in melting temperature, you can explore laser beam welding. Advantage is it's a very focused arc, no filler is required. So your dilution is going to be very minimal because you are not adding any external filler wire here. Your weld will be much better when compared to your arc weld. So you can see how the penetration comes in case of electron beam welding. It's another high potential process which can be explored for dissimilar metal welding. So this is our laser beam. So I have compared here arc welding to a laser welding. You can see how deep the penetration or how constrained the penetration is. Then you have friction stir welding. For example, you have to join aluminium to steel, which are not conventionally possible with the fusion welding. You have solutions with friction stir welding, and a lot of researches are happening today worldwide on this. And this is a typical FSW setup where you use a tool and these two metals are joined. So the biggest advantage here is it is not exposed to the melting point of the either metals, but there are a lot of associated challenges which the researchers are still working on. And this is an interesting technique which is known as, rather a process known as magnetic pulse welding, which are being used when you have intricate shapes, small intricate shapes having dissimilar metal. So the photo which I have shown is a 2 mm thick copper to stainless steel welding, and you can see how beautifully it has got joined on the micro photograph. So it's a low heat density process with excellent reproducibility, and this has been nowadays used very widely in the nuclear industry, where you have very intricate shapes to join and the materials are dissimilar. And this is a very wide application of explosion bonding, especially in the case of refineries and petrochemical plants. Then, for example, you have to have titanium or carbon steel substrate. So prima facie they are not weldable. So how to join them is by explosion bonding. And explosion bonded steel has been successfully used across industries for such critical applications. So this is one of the way to handle materials which are not weldable by fusion. So as I conclude, dissimilar metal, I need to consider 4 aspects like metallurgical, performance, welding process, and selection of welding consumable. In metallurgy aspects, this metal welding requires consideration of all the basic factors found in conventional welding. On the other hand, the difference of the base metal and weld metal chemistry should be precisely analyzed. So, the welding engineer has got a major role in handling this part. And regarding the performance, the mechanical and physical properties, microstructural stability, resistance to oxidation and corrosion of the weld metal as well as that of the heat treated zone. Generally, we are worried only about the base metal, but what is more critical in case of weld in heat treated zone. So that area should also have similar properties as that of base material, which is a very big challenge for the industry today. And the welding process which you choose depends on various enormous factors like the heat input you want to deploy, which is directly attributable to the dilution, the alloy element migration, the residual stress which you produce in the joint. All those needs to be addressed while you select the welding process. And the selection of a suitable welding consumable, which I was trying to explain in many slides, has to do a lot with your dilution and the metallurgical compatibility with the two materials which you try to join, and in order to achieve the required properties. So with this slide I conclude my presentation, and thanks to all of you for being with us today. Jörg, you are around?
Yes, I hope. And I hope you can hear me this time.
Yeah. It's pretty
Thank you very much, Krishna. Very interesting. And a very first input to the audience. I have to really apologize. We tried behind the scene to find out what caused all these issues. We got some little hint what happened wrong. Just for everybody, the chat got disabled as well. That was due to a previous big event that the Nickel Institute had. It was called the Battery Day, and there they did some changes in the settings. So you still can use the question and answer. So unfortunately, during the webinar, we cannot unlock the chat, so that will be definitely available again in the next webinar. So I have seen there is actually already one question in, and it is carbon steel to stainless steel weld with EER309L not preferred for service above 370C according to ASME section 2B. So which consumables preferred to weld stainless steel to carbon steel with service above 425 Celsius? That's for you, Krishna.
Yeah, so as you have rightly pointed out, above this temperature, this 309L is not preferred, because there is a possibility of sigma formation and embrittlement in stainless steel at that temperature. So what is generally practiced is you use an inconel filler wire, do a buttering on the carbon side, subject it to post-weld heat treatment, if the case may be. So there may be conditions or service conditions rather low, when your joint thickness is say low, for example, it is less than 38 in case of an ASME job, then you can do a buttering even without PWST. And if it is greater than 38 mm thick, you use an inconel electrode like ERNACR3 or ENACR Fe2, Fe3, do the buttering, subject it to PWST, machine it, and join your stainless steel component, and do that welding as well with an inconel electrode. So this has been proved to be very effective, and in fact you can see a lot of literatures or rather technical articles on the Nickel Institute website regarding this combination. So I recommend all of you to visit the site, go through all those technical literatures, and hundreds of years of study has been put in the form of technical literatures in that site. So please make use of it.
Absolutely, that is correct, Krishna. Thank you for mentioning it. And as you heard as well, or have seen in the beginning, in the introduction, this webinar is as well conducted by IMOA, the International Molybdenum Association. So as well on their webpage, there is a lot of information about all these kind of materials, how to perform, how to work with it. So Nickel Institute, if you go on to www.org, nickelinstitute.org, then you will see immediately a yellow banner that is called Technical Help. If you click on that one, it opens up. You can just register your name, your email address, and then you can type in any question that is related to stainless steel or even to this webinar, and you will get an answer either by Krishnan or one of our experts. So please use it, it's free of charge. And yeah, I see we get more questions in, very interesting. So there is another one for the ones that can't see the question. It's carbon steel to stainless steel clad vessels sometimes require PWHT as per code due to thickness of carbon steel and around 600 Celsius. Is it a chance to damage stainless steel clad material due to the PWHT?
Yeah, so again a very interesting question. See, what generally happens is it is not recommended, subject stainless steel to this temperature, but you cannot always avoid that in fabrication or in service. So, as a precaution, when you procure this clad steel, where you have carbon steel substrate and stainless steel exposure bonded to it, you do all the corrosion tests in the plate or in the clad plate. Okay, for example, you do practice E, practice C, depending on your application. So, subject the coupon to that temperature, that cycle, there are various tests which are being explained in ASTM. So, you need to check your base material or the clad material, whether it is meeting all those tests before you use it on the job. I think I answered that.
If there are some more questions up, then please come in. We have another one that is, oh yes, it's appreciated the very detailed presentation of you, Krishna. Yes, we will send a copy to Miss Nolia or Mrs. And she will distribute it. We will as well edit this presentation, this webinar. We cut out all the great happenings in the beginning, and we will make this video out of it, and you will get the link as well to watch it and rewatch it again. So thanks for the compliment, and yes, you will get the presentation.
Yeah, there is one.
Yeah, Krishna.
Yeah, so apart from ASME section 9, how can we recommend to carry out ferrite number check in PQR since it is not mandatory in section 9? So I would like to answer this question in such a way that what ASME section 9 depicts is only the minimum mandatory requirements. That doesn't stop, a welding expert or a fabrication guy in doing additional tests in your PQR. So my experience based on various catastrophic failures which has happened all across in disposable metal, it is very important that a ferrite check should be part of your weld procedure. Because while you select your weld consumable, whether you are getting enough ferrite, because in PQR what happens generally is it's a very small coupon. Okay, so sometimes there is a possibility that it may get through, but when you do similar procedure in the service condition, your actual conditions are totally different. So the more and more tests which you are able to incorporate in your PQR, the more safe you are while in service. So it's very important as a welding expert, we carry out ferrite in case of a dissimilar joint. Yeah, sir.
Thank you very much for this answer. Oh, there is the next one coming in.
Yeah, thanks for the answer. When I recommend to carry out a ferrite check as a client, contractor is required that it is not required as per section 9. So what we need to do is it should be part of your specification. Okay, because if you see the specifications of your leading process licenses and for all those addresses many critical requirements which they have gathered, over a period of time, which are over and above section 9. So the moment it is part of your specification, the client is very clear right from beginning that it needs to be adhered to. So they take care of that in the technical aspects, also the cost aspects. So the good practice is to make it part of the document so that client is abide to follow that requirements right from beginning. Yeah.
Yep, that is definitely very much appreciated. And let's wait another 2 minutes to see if somebody else is typing in a question.
Yeah.
Yes, it's absolutely amazing what you presented as well, how you structured it. It's interesting and keeps you listening from the beginning to the end. It's unfortunately that we had this little glitch in the beginning, but it will be definitely done next time appropriately, that from the start to the end everything will go smooth without the glitch. So there is another question.
Yeah, there's one more. Is chance of galvanic corrosion between dissimilar weld joint? Yeah, in fact, I covered this in my presentation. There's a very high possibility of galvanic corrosion, which the chances are very less in case of similar joint. But in case of dissimilar joint, since your potential is different for both the material, there's a very high chance. So there are tables available, okay, based on the potential of each of the material. So if that gap is too high, your chance of galvanic corrosion is very high. So be very careful. So the role of a welding engineer, or rather a metallurgy expert, and the designer is very crucial while you select the material combination. It should happen in tandem and should not happen, just with one department. So we need to take care of all these aspects. So to answer precisely, it is very important to take care of the galvanic corrosion aspects while you design a dissimilar weld joint. Yeah.
Yes. Okay. And during the time we wait for maybe another one, I would like to thank MISIF, especially Ms. Nolian, for setting up this webinar, getting as well all the advertisement out, reaching out to the members and the audience. So thank you very much appreciated, and I really hope that we can have soon another webinar in our series to support MISIF and the Malaysian industry when it comes to know-how on how to handle stainless steel, how to treat stainless steel, how to avoid corrosion, how to weld it, because we believe as more as we train the audience, as better the material will become. The material is already good, but we all know it's the man behind that makes it at the end fly.
Yeah, it's a very, very valid point. The discipline and the know-how which you have in converting those metals to a useful shape is the most critical part. Because if you get a good source, it is possible to get the right material. But unless you follow the good practical aspects, or rather the good practices, what you produce will not be the best one.
Correct, I fully agree with you. And with that, I would like to ask the audience as well, if you have a topic you would like to listen to, please send it to Miss Nolia and Missif, and we are more than happy to find ideas what kind of webinars we can create that the audience would like to listen to. So yes, we have our topics, but we should have new ones as well. So please feel free to let us know what you would like to hear from us. And if there are no other questions, I think we let the audience go back. I think it's already lunchtime. Stomach is calling. So again, Krishnan, thank you very much for your very interesting information. And yes, I would like to hand it over to you for your final words. But before that, once you stop the button, because I had to give you the host, just click leave for all. And for everybody, there will be, once we stop the webinar, a survey popping up. Would be absolutely fantastic if you could fill in with 3-4 questions.